Hi, this is Hilal. This is the summary video on the matrix algebra or linear algebra. The topics covered in this video will be the role of the linear algebra, definitions and terms, addition and subtraction of matrices, scalar multiplication, vector multiplication, multiplication of matrices, identity and null matrices, matrix expression of system of linear equations. Similarly, we will cover the determinants and non-singularity, third order determinants, and also cofactor and adjoint matrix. At last, we will see the inverse matrix and solving a system of linear equations using inverse matrix. And also, and not the least, we will see the Cramer's rule for matrix solution. So this is the summary video. Matrix algebra or linear algebra. Now this linear algebra permits expression of a complicated system of equations in a simplified way. If we have a system of linear equations like 4x1 plus 6x2 plus 3x3 is equal to 14, similarly we have the second equation and third equation. This matrix algebra permits us or helps us to express those system of linear equations in a simplified way or in a matrix form. This matrix form is the simplified version of this system of linear equations. So in the subsequent videos, we will see how to convert a system of linear equations in a matrix form. Second, it provides a shorthand method to determine whether a solution exists before it is attempted. Now this linear algebra or matrix algebra provides us a shortcut method to determine whether a solution exists before it is actually attempted. That is to say, we get an idea whether a solution exists or not before we actually try to solve the system of equations. So we don't have to mess up with the whole stuff. We can see whether the solution exists before we actually try to solve the system of equations. So it minimizes the process of solving the system of linear equations. Now third one is it furnishes the means of solving the equation system. Now when we got that the system of linear equations has a solution or there exists a solution, then it helps us to solve the equation system. That is to say, it helps us to solve the system of equations provided that the solution exists. There exists a solution. Now this matrix algebra can be applied to system of linear equations only. So this can be applied only to the system of linear equations. A linear equation is a one where the degree of the variable is 1. That is, the highest power of a variable is 1. Here we can see the highest power is 1 because x to the power 1 is here, the exponent is 1. Similarly, here also the exponent is 1. Here also the exponent is 1. So these are the linear equations. So we can use the matrix algebra only to the system of linear equations. But there are many economic relationships that can be approximated by linear equations, and others can be converted to linear relationships. Thus the limitation can be this limitation can be averted easily. That is to say, if we have a non-linear function, that is z is equal to, let us say, x to the power 0.5 divided by y to the power 0.2, let us say. Now this is a non-linear function. We can convert this non-linear function into a linear one by taking log on both sides. That is, log of z is equal to this. Now this will become 0.5 log of x minus 0.2 log of y. Now this is the linear equation. Now we can use the matrix algebra on this linear equation. Now how to convert the non-linear function into a linear function? We have covered this whole stuff in the logarithm portion in this mathematical economics series. Now let us have a real life example. For a company with several different shops selling several different products, a matrix provides concise way of keeping track of records. Now if I have a company and the company has 3 shops, shop first, second, third. In every shops there is an amount of pencils, books and markers. Now this helps us to keep track of the stock. That is to say, by reading across a row of the matrix, this is the matrix, this system. Now, by reading across the row of the matrix, the company can determine the level of stock of any of its shops. Now, here we can see in the shop first, total level of stock is 4 plus 3 plus is 4 plus 3 plus 2 is 7. Similarly, in shop 2 we have 5 plus 1 plus 7, that is 13. Similarly, here 2 plus 4 is 6 plus 6 is 12. So by reading across the matrix, the company can determine the level of stock of any of its shop. Similarly, by reading down a column of the matrix, the company can determine the stock of any line of its products. Now we can see the number of pencils the company has in all three shops, that is 2 plus 1 plus 4, that is 7. Similarly, here it is 2 plus 5 is 7 plus 4 is 11, and 3 plus 7 plus 6, that is 12. So every element in a matrix has a unique position, and every element is ordered according to its position. So this matrix helps us to simplify the system of linear equations. Now, matrix is a rectangular array of numbers, parameters, or variables, each of which has a carefully ordered place within the matrix. That is to say, if I have this arrangement of numbers, this array of numbers, I can have here the parameters. Here I have taken the numbers. Now, every number has a carefully ordered place within the matrix. That is to say, every number has been carefully ordered. So this is not a randomization. Every element has a carefully ordered place within the matrix. Now, numbers, parameters, or variables. In this, here these are the numbers. In place of numbers, there can be the parameters or variables. So these are called the elements of the matrix. So this 4, 8, 7, 2, 1, 6, these are the elements of the matrix. These are the elements of this matrix. Similarly, this 2 is also the element, 6 is also, 7 and 1 also. Now, dimension of a matrix. What is the dimension of the matrix? Number of rows multiplied by the number of columns gives us the dimension of the matrix. That is to say, here the number of rows is 1 and 2. There are 2 rows. Similarly, number of columns is 1, 2, 3. So I can say dimension of this matrix is, that is, dimension of this matrix is number of rows, that is 1 and 2. There are 2 rows. So I will write here 2 times the number of columns 1, 2 and 3. So here the dimension of the matrix is nothing but the number of rows multiplied by the number of columns. Now, row number always precedes the column number. This row number always precedes the column number. First we write the row, that is to say R cross C. So first we write this R, and then after R we multiply by C. We can't interchange the positions here. So this precedes, row always precedes the columns. Here it is 2 cross 3. This means the first 2 is the number of rows, and the second one, here it is 3, depicts the number of columns. So this row always precedes the columns. Now in a square matrix, number of rows is equal to number of columns. If I have a square matrix, let us say 1, 4, 6, 2, 3, 8, 9, 4, 1. Here number of rows is 1, 2 and 3. So 3. Number of columns is 1, 2 and 3. So the dimension of this matrix is 3 by 3. So in a square matrix, number of rows is equal to the number of columns. Now column vector. Column vector is composed of single column and it is written as R cross 1. That is to say, column vector, if I have a matrix, let us say B is a matrix. If I have the number column like 1, 2, 3. This matrix is composed of single column. Here the number of rows is 1, 2 and 3, but column is only 1. So this is written as R cross 1. Since the number of rows here is 1, 2 and 3, so I will write here 3 by 1. So this is a column vector. Column vector. Now row vector. Row vector is composed of a single row. Row vector is composed of a single row. That is to say, if I have another, let us say I have E is a matrix, and here I have the elements 1, 4, 6. Now this row vector is composed of single row. Here the number of rows is only 1. So the dimension of a row vector is 1 cross C. 1 by C. That means I have a single row and here the number of columns is 1, 2 and 3. So here the dimension of this matrix is 1 cross 3. So this is the row vector. Row vector. This is the row vector here. Now if I give another example, let us say I will place a general matrix here. That is, if I have a matrix, general matrix, let us say A is equal to A11, A12, A13, A21, A22, A23. Similarly, A31, A32 and A33. Now this is a general matrix composed of, that is 3 cross 3. That is, number of rows here are 3 and number of columns is 3. So the dimension of this matrix is 3 cross 3. Now it is a square matrix here, and one thing is to be remembered, these elements are not punctuated. These are not separated by the punctuation marks. Now the elements have the double subscript here. Like here it is A11, A12. This subscript here gives us a unique position or address of any element. This gives us the unique position of any element. Now if I have this this element here, that is A21, this 2 tells us the position in the row. That is, this is first and second. This says this is at second row, and this one says this element is in the first column. Similarly, if I have here A2, 3, this 2 tells us that the address of this element is at the second row, that is first, second. So this tells us it is in the second row, and this 3 tells us it is in the first, second and third column. So these subscripts give us the address or placement of element in a matrix. Let us say another example, if I have this A2, A32, this gives us the position, that is here, this gives us the position in which row the element is. Here the row is first, second and third, so this gives us position in position of row, and this gives us the position of column, so these two give us the address, this address of this element. Here the address of this element is, it is in the first, second and it is in third row and second column. So this is the row position and this is the column position here. Now if I have another example, let us say if I have another general matrix, B is equal to A11, A12, A21, A22. So this subscript tells us that the element here is in the second row, that is this 2, and in the first column. This gives us the address of the matrix. These subscripts give us the address of the matrix. So to determine the number of rows, always count down. We always count down. And to determine the number of columns, always we count across, that is we count across. So if we count down like this, so this gives us the number of rows. Now if I have a general matrix, that is A is equal to A11, A12, A13, similarly A21, A22, A23 and A31, A32, A33. Now this double subscript gives us this subscript to an element here gives us the address or placement of the element within the matrix. That is to say, the first subscript here, if I have this number here, this subscript, this first subscript identifies the row in which the element appears. So here the first subscript is 2, so this identifies the row, that is this 2 represents that this element is in first and second, this element is in second row. Similarly, this second here, this subscript identifies the column, so this tells us this element is in column first. Similarly, if I have here A23, this 2 identifies the row, that is first, second, we are in the second row here, and this 3 identifies the column. So here we are in column first, second and third, we are in column third and second row. So every subscript gives us the position of the element within the matrix. If I have another example, like if I have A11, A12, A21 and A22. Now this 2 tells us that this element is in first and this is in second row, and this one tells us we are in first, this element is in first column. So these subscripts gives us the address or placement of the matrix within the matrix. Here if I give another example, here it is A33. This first 3 tells us the position of the row, that is first, second, 3. This tells us the element is in the third row, and this second 3 tells us this element is at third column also, first, second and third. Now if we will see that transpose of a matrix, if I have this this is A is equal to this general matrix. Now the transpose of this element is, if we interchange columns with numbers, we will be transposing this element. Now the transpose of a matrix is interchanging rows with columns. If I have this general matrix, now the transpose of this matrix is denoted by, that is, A dash. This A dash means the transpose of this general matrix. Now transpose is interchanging the rows with columns. If I have here the rows, here these are the rows, if I interchange them with columns, so these rows will become the columns. So here it will become A11, A12, A13. We have placed rows in place of columns, and we have replaced columns with rows. So here these were the rows, and we have placed them in columns. Similarly, this will become A21, A22, A23. Similarly, A31, A32, and A33. A31, A32, and A33. So we have interchanged the position of rows with columns. If I have an example, let us say I have A is equal to, or let us say I have B is a matrix like 1, 4, 1, 6, 7, 8, 5, 9. If this is the matrix, now transpose of this matrix is denoted by B dash. Here I will transpose the rows with columns. So here this will become 1, 6, 7, and 8, 5, 9. So the transpose of this B is this matrix is this. I have interchanged rows with columns. Similarly, if I have another matrix, let us say E is equal to 1, 4, 6. Now the transpose of this is E dash. That means I will change it by column. So this will become 1, 4, 6. I have interchanged the positions here. Similarly, if I have another, let us say D is a matrix, that is column matrix 1, 4, and the transpose of this will be D dash. That is, I will interchange them with the rows. So this will become, row will become column, and column will become row. Here this will become 1 and 4. So interchanging the rows with columns gives us the transpose of a matrix. Now addition and subtraction of matrices. Now addition or subtraction of two matrices requires that the matrices be of equal dimensions. That is to say, we can add or subtract two matrices only when they are of equal dimensions. Let's have an example. If I have the matrix, let us say A is equal to 1, 4, 6, 2, 8, and I have another matrix, that is B is equal to 1, 7, 8, 9. Now the dimension of this matrix is, as we have seen, the dimension is number of rows times number of columns. Here the number of rows is first, second. The number of rows is 1, 2. So the dimension is 2 by the number of columns, first and second. So there are 2 rows and 2 columns. So this 2 by 2 gives us the dimension of this matrix. Similarly, here the number of rows is 1 and 2 by the column number of columns is 1 and 2. So we can add these two matrices because they are of equal dimensions. Now addition is done by like this. Each element of one matrix is added to the corresponding element of other matrix. That is, this element 4 will be added to this element. this corresponding to this element. Similarly, this 2 will be added to this 7 and 8 will be added to this 9. So this 4 cannot be added with 9. Every element is added with its corresponding element. So the matrix, if I add here, that is A plus B is equal to, that is 4 plus 1, 4 plus 1. Here it is 2 plus 7, 2 plus 7. Similarly, here is 6 plus 8, 6 plus 8. Similarly, 8 plus 9, 8 plus 9. So this will become, now 4 plus 1 is 5. This will become 9. This will become 14 and this will become 17. So A plus B is equal to, that is the addition of these two matrices will give us this matrix. Similarly, we can subtract them also. That is 4 minus 1, that is 4 minus 1. Here it is 2 minus 7, 2 minus 7. Here it is 6 minus 8, 6 minus 8, and here it is 8 minus 9. So this will become 4 minus 1 is 3, this 2 minus 7 is minus 5, 6 minus 8 is minus 2, and 8 minus 9 is minus 1. So this is the addition of these two matrices, and this is the subtraction of these two matrices. Now we have a topic, that is scalar multiplication. In matrix algebra, a simple number, let us say we have 4 minus 2 or 0.3. These simple numbers, these numbers are called scalar. These are called scalars. Now multiplication of a matrix by a number or a scalar involves multiplication of every element of the matrix by that number. That is to say, if I have a matrix, let us say if I have A is equal to 1, 4, 6, 2. This is a matrix. Now multiplying this matrix by a scalar means, if I multiply this A here, that is 2 times A. Now I have multiplied this matrix by this 2, which means I have to multiply this 2 with every element. That is, this will become 2 into 1 here, because I am multiplying this by 2 here, this scalar. So here it is 2 into 6, here this is 2 into 4, here it is 2 into 2. So this will become 2 ones are 2, this is 12, this is 8, and this is 4. So this scalar, this is called the scalar multiplication, because it scales the matrix up or down. Here this scales the matrix up. If this was the matrix, it scales this up because we have multiplied it by the 2. If I multiply this, let us say I have the same example, and if I multiply this by minus 2, so this will become minus 2 into 1, minus 2 into 6, and minus 2 into 4, minus 2 into 2. That will give us minus 2, minus 8, minus 12, minus 4. So this is called scalar multiplication, because it either scales up the matrix, because this matrix has been scaled up. Every element has been scaled up. That is, if it is here 1 and it increases to 2, similarly 4 increases to 8. So this scales up here. Similarly here, if I have this example and if I have multiplied it by a scalar, that's minus 2, here this has scaled down the original matrix, because 1 is greater than 2. So there is a downward shift, or we have scaled down the original matrix. So it is very easy to multiply by a scalar. If I have another example, let us say I have A, and this is some constant in general. A is equal to 1, 2, 4, 6. Now scalar multiplication means if I have this scalar quantity A, so this will become 1k into 1, that is 1 in k into 1, k into 4, k into 2, and k into 6. So this will become k, 4k, 2k, and 6k. So multiplying by a scalar, either scales up or scales down the matrix, the size of the matrix. Now in case of 1, if I multiply this by 1, so 1 will neither scale up or scale down the matrix. Now vector multiplication means multiplying a row vector A by a column vector B, that is multiplying a row vector by a column vector. Now this multiplication is only possible when each vector has same number of elements. That is, if I have a row vector A is equal to, let us say this is 2, 3, 5, and I have another column vector that is B is equal to 1, 2, and 4. Now I can multiply these two vectors only when the number of elements in each vector are same. Since the number of elements in this column vector are 3, that is 1, 2, and 3. Similarly, here the number of elements are 3, that is 1, 2, and 3. So I can multiply these two vectors. If the number of elements are not same in both the vectors, then we cannot do the multiplication. So this is the condition or condition on multiplying the vectors. Now then the product is found by multiplying the individual elements of row vector by their corresponding elements in the column vector, and then summing the products. That is, if I have to multiply these two, I will write like this. This is A, B. So this A, B means I am multiplying these two. This will be equal to, now my row vector is 2, 3, 5, and my column vector is 1, 2, 4. That will be equal to, now I have to multiply the individual element of row vector with its corresponding element in the column vector. That is, we can, the product is formed by, I will multiply this 2 with this 1, that is 2 into this 1 plus I will multiply this 3 with this 2, that is 3 into 2 plus this 5 with this corresponding 4. So this is 5 and this is multiplying this with 4. So this will become, now this is 2 ones are 2 plus 3 twos are 6 plus 5 fours are 20. So this will become 26 plus 2, that is 28. So I will write here, this is 28. So I have multiplied the row vector with column vector. So the condition is that the number of elements in both the vectors must be equal. Now this product of row column vector gives us a single number. That is, when I multiply this row vector with this column vector, I got a single number, that is 28, which is a scalar. This is scalar here. So multiplying row vector with a column vector gives us a single number or a scalar. Now this row column multiplication is very important because it serves for the basis of matrix multiplication. Now in the next video we will see the matrix multiplication. There we use this row column multiplication. An example on the vector multiplication, that is row column multiplication, is like this. Assume Q is a row vector of physical quantities of pencils, books and erasers sold respectively on a given day, and P is a column vector of corresponding prices of pencils, books and erasers, that is given as Q is 4, 5, 3, and P, that is column vector, is 2, 10 and 3. These are the quantities of pencils, books and erasers sold, and these are the corresponding prices of the pencils, books and erasers. Find total value of sales. Now we can find the total value of sales by multiplying these two vectors. Since the number of elements in each row are equal, therefore we can easily multiply these two vectors. Therefore total value of sales will be total value of sales is equal to, that is total value of sales is equal to price, quantity times price, that is Q into P. Now Q is given as 4, 5, 3, and we will multiply this by P. The P is 2, 10 and 3. Now we will multiply the corresponding element in row with its corresponding element in the column, and then summing the product. That is, as we have seen in the earlier example. Now this is, we will multiply this 4 with the corresponding element here, that is 2. This is 4 into 2 plus this 5 is multiplied with this 10. This is 5 and 5 into 10 plus, and this 3 is multiplied with its corresponding element, that is 3 here. So this is 3 into 3. Now this will become 4 2s are 8 plus this is 50 plus 9. Now this will become, now this is 59, 59 plus 8, that is 67. Therefore total value of sales is 67. So this was an example on the row column multiplication. Matrix multiplication requires, the first condition is that matrices must be conformable. Conformable means that the number of columns in the first matrix, if we are given the two matrices, this A matrix and B matrix, then the number of columns in the first matrix, which is called the lead matrix also, must be equal to the number of rows in the second matrix, which is called the lag matrix. Now here we can see the number of columns are 1, 2 and 3, and here the number of rows are 1, 2 and 3. Since the number of columns in the first matrix are equal to the number of rows in the second matrix, then these two matrices are conformable. Then we can multiply these two matrices. Now a general formula for seeing whether the matrices are conformable or not, if we are given the matrices, first matrix is of dimension m times n, and the second matrix is of dimension n times p. Now what will we do? We will encircle these two these two elements or numbers here. Since these two are equal here, this means the two matrices are conformable, and the resulting matrices is of dimension, that is m cross p. In the earlier videos I have explained what is the dimension of a matrices. Dimension of matrices is the number of rows multiplied by the number of columns. Now if we apply this on this formula on the given example, here the dimension of this matrices is number of rows are here 2 and number of columns are 1, 2 and 3. Similarly here the number of rows are 1, 2 and 3 and the number of columns are 1 and 2. Now if we apply this formula on this, that is the dimension of this matrices is 2 by 3 and the dimension of this matrices is 3 by 2. Therefore we can see here 2 into 3, and I will write the dimension of this like 3 into 2. Since these two numbers are equal, then these two matrices are conformable, and the resulting matrix after multiplication will be of dimension 2 by 2. So this is an example of the two matrices which are conformable. Now if I have another example, let us say I have an example. I have a matrix A is equal to, that is, let us say it is 2, 3, 4, 1, 5, 6, and I have second matrices, that is B is equal to 1, 4, 2, 6, 4, 0, let us say. Now if I apply the same formula, that is m cross n and n cross p, now these two numbers must be equal. Now here the dimension is here 1, 2 and 3. Number of rows are 3, and the number of columns are 2. Here the dimension is also same, 3 rows and 1 and 2 columns. Now to see whether these two matrices are conformable or not, we will apply this formula or visualization method. Now here this is 3 into 2, here also 3 into 2. Now we can see here these two numbers are not equal. Therefore we can say that we can't multiply these two matrices. So these matrices are non-conformable here. So the first condition to multiply any two matrices is to see whether the two matrices are conformable or not. Conformable means the number of columns in the first matrices must be equal to the number of rows in the second matrix. Here we can see the number of columns are here 2 in the first matrix, but the number of rows here are 1, 2 and 3. So these two are not conformable. Now after being sure that the two matrices are conformable, we can go for the matrix multiplication. In this case, these two matrices are conformable because the number of columns in the first matrices are equal to the number of rows in the second matrix. Here the number of columns are 3 and then here the number of rows are also 3. Now after that, each row vector in the first matrix, that is the lead matrix, is then multiplied by each column vector of the lag matrix. Now each row vector here is multiplied with this column vector, that is row vector of the first matrix is multiplied with the column vector of the second matrix. Now this is to be remembered that use only rows from the first matrix and columns from the second matrix. We have to use rows from the first matrix and columns from the second matrix, and not the columns from the second matrix and rows from the first matrix. We have to use only rows from this matrix and columns from this matrix to multiply the matrices. Now row column products, this row column products are also called inner products or dot products. Now these row column vectors are then used as elements in the formation of product matrix. Now we will see. Here I have denoted these columns by C1, C2 and C3 and rows by R1 and R2. Similarly, I have done the same here. Now, making sure that we use only rows from the first matrix and column from the second matrix. Then the matrix multiplication is done by first we take row of the first matrix and we multiply this by the column of the leg matrix to find the element of first element. Now we have to multiply the first row, that is R1 of the lead matrix, with the first column of the leg matrix, that is R1 C1, that is this R1 row and C1 column to get the first element. After that we take the first row of the lead matrix and we multiply it by the second column of the leg matrix to get the second element, this element. Similarly, since there are no more columns left in this leg matrix to be multiplied by the first row of the lead matrix, now we will move to the second row, that is we will multiply the second row of the lead matrix with the first column of the leg matrix, that is R2 and C1, R2 times C1 to get this element, third element. Similarly, we take the second row of the lead element and we multiply it by the second column of the leg element to get this, to get the fourth element of the matrix. Now we will see how it is done. It is here. Let's I place this here. This will become A into B, that is A times B is equal to, now I have to multiply the row 1 of the first matrix. This is this row with this column, so this will become 1 into 2, that is 1 into 2 plus 3 into 1, that is 3 into 1 plus 2 into 3 plus 2 into 3. Now this is the first element. Similarly I will take the row 1 and column 2, that is row 1 and column 2. So row 1 will be multiplied with this column 2. This is 1 into 3, so this is 1 into 3. Now 3 into 4, this is 3 into 4 and 2 into 0 plus 2 into 0. Similarly, we have to take row 2, that is this row and the first column. So this will become 4 into 2, that is 4 into 2 plus 1 into 1, 1 into 1 plus 5 into 3 plus 5 into 3. So this is the third element. Then R2 C2. Now row 2 and C2. This is 4 into 3, this and this, plus 1 into 4, 1 into 4 plus 5 into 0 plus 5 into 0. So this will become, now this is 2 ones are 2 plus 3 ones are 3. So this is 2 plus 3 plus 6. That is 2 plus 3 is 5. 5 plus 6 is 11. So this is 11. Here 3 ones are 3. 3 fours are 12. So this is 3 plus 12 is 15. And 15 plus 2 into 0. This is 0. So this is only 15 here. Similarly, this is 4 twos are 8 plus 1 ones are 1 plus 5 threes are 15. So this is 8 plus 1 plus 15. So this will become 8 and 1 is 9 and 9 and 15 are 24. So I will write here 24. Similarly, this is 12 and this is 1 fours are 4. So 12 plus 4 is 16 plus 5 into 0. This is 0. So here it is 16. So AB is equal to 11, 15, 24 and 16. So this is the matrix multiplication, and only one thing is to be remembered, that is we have to use the rows of the first matrix and columns from the second matrix. Now we have seen if these two matrices were, these were the conformable matrix, because the dimension of this matrices was 1, 2, number of rows were 2 and columns were 3. Similarly here the number of rows were 1, 2 and 3 and the number of columns were 1 and 2. Now since these were, this is to be remembered, for conformability we take this dimension, that is 2 into 3, and the dimension of the second, that is 3 into 2. Since these two are equal, then we can say that these two matrices are conformable. I am repeating the important points. Now the resulting matrix was this. These two left out numbers, that is 2 cross 2, which we got here. This is 2 cross 2. So this was all about the matrix multiplication. Next one is the identity matrix. An identity matrix, that is denoted by this capital I, is a square matrix which has 1 for every element on the principal diagonal from left to right and 0 everywhere else. Now identity matrix is a square matrix, like here in this example this is a square matrix and this is also an identity matrix. Now in an identity matrix there are only ones, that is 1, 1 and 1 on the principal diagonal. This diagonal is called the principal diagonal, and 0 everywhere else. Here we can see there are only zeros except for the principal diagonal where we have only one. So this is an identity matrix. Now if there is a subscript with this I, this means this is an identity matrix of dimension 3. That means it has three rows and 3 columns. So this is an example of the identity matrix. So this subscript, if I have I n, this n denotes the dimension of identity matrix, that is I. Now, multiplication of a matrix by an identity matrix leaves the original matrix unchanged. That is, if A is a matrix, if we multiply this by an identity matrix, then we get the answer A, that is the original matrix. That is, A multiplied by identity matrix gives us A. That is, we get the original matrix. Now, if I have an example, let us say I have A is 1, let us say it is 3, it is 2, and it is 4, and I is, that is the identity matrix, let us say it is 1 0 0 1, because the elements on the principal diagonal are 1 and others are 0. Now if we multiply these two elements, that is A multiplying by A times I, that means now A is our this matrix, that is 1 3 2 4, and multiplying this by this identity matrix, that is 1 0 0 1. Now the multiplication, we have covered this, how to multiply the two matrices. Now here we will see what does the result come out. Now first we multiply by first row and first column, so this is 1 into 1, 1 into 1 plus 3 into 0, that is 3 into 0. So first row and first column. Similarly, first row and second column, that is 1 0, that is 1 into 0 plus 3 into 1, 3 into 1. So this was first row, first column, the element was written here. Similarly, first row, second column, the element is written here. Now we are done with this first row. Now we will take the second row. Now similarly, second row, first column, this is 2 into 1 plus this 4 into this 0. So this is second row, first column. Similarly here we have second row and second column. This is 2 into 0, 2 into 0 plus 4 into 1, 4 into 1. Now solving this, this is here 1 1s are 1, this 3 zeros are 0, so here it is 0, here 2 1s are 2, and here it is 4 zeros are 0, so this is 0 here. Similarly here 1 zeros are 0 plus 3 1s are 3, so we get here 3. Similarly 2 zeros are 0, and here 4 1s are 4. So we can see A times the identity matrix gives us this 1 2 3 4, which is the original matrix. So we got the original matrix. That implies A times this matrix, identity matrix, gives us the original matrix. Now we have the symmetric matrix. Any matrix for which A is equal to A transpose is a symmetric matrix. That is, if I have this matrix, that is A, and if I transpose this matrix, transpose means interchanging the rows with the columns. If it is here row, we change this by the column, we write it as column. Then let us say A dash means the transpose of this matrix. Now interchanging this implies we write this row as column. So this is 1, here it is 1 minus 1 and 5. This row we wrote it as the column. Similarly we will write this row as column, that is minus 1 2 1. Similarly this row we will write it as column, that is 5 1 3. Now in this example we can see that the original matrix and its transpose are same, that is A is equal to A dash. Now whenever the transpose of a matrix is equal to the original matrix, we say that the given matrix is the symmetric matrix, because here we see these two matrices are same. Now idempotent matrix, a symmetric matrix for which A times A is equal to A, that is multiplying two symmetric matrix gives us the symmetric matrix, is called an idempotent matrix. If I have this matrix which is also symmetric here, because if I interchange the row by the column, we will get the same result, we will get the same matrix. So this is a symmetric matrix. Now if multiplying the two symmetric matrix, that is A into A, means multiplying this by itself, that is 2 minus 2 minus 4 minus 1 3 4 1 minus 2 and minus 3. Now multiplying it by itself, that is 2 minus 2 and minus 4 minus 1 3 4 1 minus 2 and minus 3. Now multiplying this, as we know the multiplication rule is, we take the first row and multiply it by the first column, that is this row and this column. So this will give us 2 into, this is 2 into 2 is 4, so I will write here 4. Similarly minus 2 and minus 1, minus 2 times minus 1, that is plus 2. Similarly minus 4 times 1, that is minus 4. So this was first row, first column. Similarly first row, second column, that is 2 into minus 2, that is minus 4. Similarly minus 2 into 3, that is minus 6. Similarly minus 4 into minus 2, that is plus 8. Now similarly first row and third column, that is 2 into minus 4, so that is minus 8. Now minus 2 into 4, that is minus 2 into 4, that is minus 8, and minus 4 into minus 3, that is plus 12. Similarly second row, first column, that is minus 1 into 2, that is minus 2. Now 3 into minus 1, that is minus 3. Similarly 4 into 1, that is 4 into 1 is 1. Sorry, 4 into 1 is 4. Similarly second row and second column, that is minus 1 into minus 2, that is plus 2. Similarly 3 into 3, that is 9. Similarly 4 into minus 2, that is minus 8. Now second row, third column, that is minus 1 into minus 4, that is 4. 3 into 4, that is 12, and 4 into minus 3, that is minus 12 here. Now after the first row, second row, we will see the third row, first column, third row, second column, third row, third column. So here it is 1 into 2, that is 2. Minus 2 into minus 1, that is plus 2. And minus 3 into 1, that is minus 3. Similarly third row, second column, that is 1 into minus 2. 1 into minus 2, that is minus 2. Minus 2 into 3, that is minus 2 into 3, that is minus 6. Minus 6. Similarly minus 3 into minus 2, that is plus 6. Sorry, plus 6 is here. Similarly third row, third column, that is 1 into minus 4, that is minus 4. Minus 2 into 4, that is minus 8. Minus 8. Similarly minus 3 into minus 3, that is plus 9. Now further solving this will give us, now this is 4 plus 2 is 8, sorry, 4 plus 2 is 6 minus 4, that is 2, or I will write here it is for clarity. So this is 6 minus 4, that is 2. Here we have minus 2 minus 3 is minus 5 plus 4, that is minus 1. Similarly 2 plus 2 is 4 minus 3 is 1. Here minus 4 minus 6 is 10. Minus 10 plus 8, that is minus 2. And 9 plus 2 is 11. Minus 3, that is minus 8, that is 3. Similarly minus 6 minus 2 is 8. Minus 8 plus 6, that is minus 2. Here minus 8 is 16. Minus 16 plus 12, that is minus 4. And 12 plus 4 is 16. Minus 12, that is 4. And 8 plus 4, minus 4 minus 8 is minus 12 plus 9 gives us minus 3. Here we can see we got the original matrix. That is, when we multiply this matrix by itself, we got the original matrix, which is equal to A. Implies A times A is equal to A, where A is a symmetric matrix. Symmetric matrix. Now symmetric, I repeat, symmetric is a matrix. Symmetric matrix is a matrix where if A is a symmetric matrix, then its transpose is, that is interchanging rows with columns. So this will become this 2 minus 2 and minus 4. Similarly minus 1 3 and 4, and minus 1 2 and 3. Sorry, 1 minus 2 minus 3, 1 minus 2 minus 3. Here we can see these two matrices are same. After we transpose the original matrix, we got the original matrix. Symmetric matrix is a matrix where A is equal to A transpose. That is, there is no change in the matrix if we interchange the rows with the columns. Then that matrix is called the symmetric matrix. Now we have the null matrix. A matrix composed of all zeros and can be of any dimension. Any matrix where the elements are only 0 is called a null matrix. That is, if A, let us say A is equal to 0 0 0 0 0 0 0 0. So this is a null matrix where all the elements are 0. Now a null matrix can be of any dimension. It is not necessary that a null matrix must be a square matrix. Here we can have a rectangular matrix also, which is also a null matrix, that is 0 0 0 0 0 0. So this is also a null matrix. Now addition or subtraction of the null matrix leaves the original matrix unchanged. That is, if A is a null matrix, that is, let us say 0 0 0 0. If I have another matrix, that is B is equal to 1 2 3 4. Now if I add these two, that is A plus B, this will give us, now 0 plus 1 is 1, 0 plus 2 is 2, similarly 0 plus 3 is 3, and here 0 plus 4 is 4. So adding a null matrix to any matrix leaves the original matrix unchanged. Similar is case with the subtraction. So it leaves the original matrix unchanged if we add or subtract the original matrix by a null matrix. But multiplying by a null matrix produces null matrix. That is, let us rub this out. If I have a null matrix, let us say A is equal to 0 0 0 0, and if I have another matrix, that is B is 1, 2, 3, 4. Now if I multiply these two, that is AB is equal to 0, 0, 0, 0, and B is 1, 2, 3, 4. Now if I multiply, as we have seen in the rules of multiplication, that is first row, first column, that is 0 into 1, 0 into 1, plus 0 into 3, plus 0 into 3. Similarly, first row, second column, that is 0 into 2, plus 0 into 4, 0 into 0 into 4. Similarly, second row, first column, that is 0 into 1, plus 0 into 3, 0 into 3. Second row, second column, that is 0 into 2, plus 0 into 4. Now the result is here 0, 0 times anything is 0, so this whole will become 0, 0, 0, 0. That is multiplying by a null matrix produces a null matrix. Here we can see AB is equal to this matrix, that is null matrix. Null matrix. How to express a system of linear equations in matrix form. Now this matrix algebra or linear algebra helps us or permits the concise expression of system of linear equations. That is, if we are given a system of linear equations, we can convert those system of linear equations in matrix form. Let us have an example. We will see how to express a system of linear equations in matrix form. If I have the system of linear equations like I have 2x1 plus 3x2 is equal to 8, and another linear equation is that is 4x1 plus 5x2 is equal to, let us say this is 12. Now these are the system of linear equations. Now this system of linear equations can be expressed in matrix form like, that is, this can be expressed in matrix form like, this can be converted into matrix form like A x is equal to B, where this A is coefficient matrix, this is coefficient matrix, and this x is the solution vector, this is the solution vector, and this b is the vector of constant terms, vector of constant terms. Now this A is the coefficient matrix, that is A is equal to, this A is a matrix where we take the coefficients of the variables. Now in the first row we take the coefficients of x1 and x2, that is the coefficient of x1 is 2, similarly the coefficient of x2 is 3 here. In the second equation the coefficient of x1 is 4, so I will write here 4, and similarly the coefficient of x2 is 5. So this A gives us the coefficient matrix, where the first row are the coefficients of the first linear equation, and the second row, in second row we have the coefficients of second linear equation. Okay, now this x is solution vector. Solution vector means x is equal to, so this x gives us the value of, this is x1 and x2. In the x we take the column vector of x1 and x2. Similarly b is vector of constant terms, that is b is a vector of constant terms. Now the constant terms here is 8 and 12, so this is the vector of these constant terms, that is 8 and 12. So this is the way how we can express a system of linear equations in matrix form. Now, one thing is to be remembered here. This x and b will always be column vectors. These are always column vectors. Now, if I give another example, if I have another system of linear equations, to make my point clear, that is, I have another system of linear equations. Let us say I have 2x1 plus 3x2 plus 5x3 is equal to 18. Second linear equation is x1 plus 4x2 plus x3 is equal to, let us say, 10. And third one is x1 plus 9x2 plus 7x3 is equal to 30. If these are a system of linear equations, we can convert these system of linear equations in matrix form by, as we have seen in the earlier example, we write this in the form of A x is equal to B, where A is the coefficient matrix, x is the solution vector, and this B is the vector of constant terms. This is vector of constant terms. So I am abbreviating this. Actually, we have to, it is only for the sake of simplicity that this A I denote by the coefficient matrix. This A is the coefficient matrix, and x is the solution vector, and B is the vector of constant terms. Now, the first A is equal to, this A is the coefficient of matrices, that is coefficient of these linear equations. Now this first row will give us the coefficient of these equations, these variables. Now the coefficient of x1 here is 2, here it is 3, here it is 5. Similarly, here it is 1, the coefficient of x1 is 1, here the coefficient is 4, here it is 1. Similarly, here it is 1, 9, and here it is 7. So this is A. Now our solution vector here will be, the x1, x2, and x3, and our B is the vector of constant terms. Now there it is 18, 10, and 30. So 18, 10, and 30. Here we can also see these x's and b's, that is the solution vector and vector of constant terms, will be always the column vectors. Okay, I hope I make myself clear. The determinant, that is denoted by this symbol A, of a 2 by 2 matrix called second order determinant. Now if we have a 2 by 2 matrix, then the determinant of the 2 by 2 matrix is also called the second order determinant. Now this is derived by taking the product of the two elements on the principal diagonal. We take the product of the two elements on the principal diagonal. This diagonal, this diagonal, which is like the backward slash, this is called the principal diagonal, and this one is the non-principal diagonal. We take the product of the elements, two elements on the principal diagonal, and we subtract from it the product of elements on the non-principal diagonal. That is, determinant is denoted by this symbol, and it is not to be confused by the absolute value. So this whole is the determinant symbol, and this is not the absolute value. Now this is given by, if I write this again, this is A11, here A2, 2. These are the two elements on the principal diagonal, and here I have A12 and here A21. Now I multiply these two elements on the principal diagonal that is I multiply this a11 with this a22 and then subtract from it the product of these two non-principal elements, two elements on the non-principal diagonal. That is, the determinant is then a11 times a22 minus a21 a21 multiplied by a12. That is, if I have an example, if I have a matrix of 2 by 2 dimension, let us say I have a matrix that is B is equal to 1 4 2 3. Now the determinant of this B is equal to, I will multiply these two elements on the principal diagonal, that is 1 into 3 minus, I will subtract from it the product of these two elements on the non-principal diagonal, that is 2 into 4. So this will become 3 minus 8 and this is equal to minus 5. So the determinant here is B. So this is not to be confused with the absolute value. If it were the absolute value, then this minus 5 would have been the plus 5. So this is the symbol for the determinant and it is not the absolute value here, because we also denote, if I have x like in the algebra, this or in the calculus, these two lines and between them if a variable is, this is the absolute value. But in matrix connotation, this doesn't mean this is the absolute value. Now the determinant is a scalar or it is a simple number. Here we see when we got the determinant, it is a simple number or a scalar. So when we found the determinant is a scalar or a number. It is a simple number here when we take. Now if the value of determinant is 0, that is, if determinant is equal to 0, that is, if the value of a after solving this is 0, then we say matrix is non-singular. Sorry, matrix is singular. Now this singular matrix is a one in which there exists linear dependence between at least two rows or columns. That is, if I have a matrix like this, if I have a matrix, let us say 3 2 6 4, if I have this matrix, now this singular matrix is a one in which there exists linear dependence between at least two rows or columns. Now here we can see, if this is the first row and this is the second row, here we can see that this 3 is scaled to 2 and this becomes 6. Similarly, this 2 is scaled to a factor 2 and this becomes 4. So these are dependent. There is a linear dependence between, because here the factor is same. These are factored by 2. So this matrix is a singular matrix. This matrix is because 6 and 4 are factored by a number 2. But on the contrary, if I have another matrix, let us say 1 2 3 and 10. Now this 1 is factored, this 3 is factored by 3, but this 10 is factored by 5, so there is not a common factor for these 3 and 10, because here these both are factored by 2. Here these both are not factored by the same number, so I can say this is a non-singular matrix. Now we can see here the determinant of this matrix is, that is 3 into 4. Let us say if it was C is equal to, and this is D, this is the matrix C, and this is D. Here we can see the determinant of this C is equal to, this is 3 4s are 12 minus 6 2s are 12, so here the determinant is 0. When the determinant is 0, we say the matrix is singular. But when the determinant is greater than, or sorry, if the determinant is not equal to 0, let us say here the determinant of the D matrix is, now here is 10 ones are 10 minus 3 2s are 6. Here we see the determinant is 4, so D is equal to 4, which is not equal to 0. So if determinant is equal to 0, matrix is singular. And if determinant is, so I will write here, if determinant is not equal to 0, we say matrix is non-singular. Now we can have another example of the linear dependence. Linear dependence also means if there is linear dependence, there are infinite number of solutions. That means if I have a system of linear equations, so I will rub this here. Like, and I will take this out. Now if I have a system of linear equations, that is 3x1 plus 2x2 is equal to, let us say this is equal to 6, and second is 6x1 plus 4x2 is equal to 12. Now if we solve these two, let this be equation first and let this be equation second. Now to make the coefficient the same, we will multiply this first equation by 2. So we will multiply the first equation by this factor 2. So this will become 6x1 plus 4x2 is equal to, now here it is also 2 6 are 12. Let this be equation third. Now we will subtract these two equations, subtracting equation 3 from 2. Now if I subtract, now here it is 6x1 minus 6x1, so this is 0. Similarly, if I subtract these two, so this will 4x2 minus 4x2, so this is also here, this is also here 0, and here we have 12 minus 12, so this will become 0 is equal to 0. So we cannot, we have not a unique solution here. This system of equations have infinite number of solutions. These system of equations have infinite number of solutions. That means these two equations are linearly dependent. Or if I have the graph, if I depict this graphically, and if this is the equation for the first equation, that is 3x1 plus 2x2 is equal to 6, this equation is also for the second equation, that is 6x1 plus 4x2 is equal to 12. So I can say if these if there is linear dependence between the two system of equations, then we have infinite number of solutions. Now in matrix, that means if determinant is equal to 0, implies we have a matrix that is non-singular. Sorry, that is singular. Implies matrix is singular. Now we can see here also, if I depict this coefficient matrix here. So first I will rub this. If I take these two, if I take the coefficient matrix here, that is 3, 2, 6, 4. Now the determinant of this is, let us say this is the coefficient matrix A. Now the determinant of this is now 3 into 4. 3 4s are 12 minus 6 2s are 12. Now here we can see the determinant is 0, implies this matrix is singular. This matrix is singular. If the matrix is singular, means there is linear dependence. Now there is linear dependence. These means, now if the matrix is non-singular, if the determinant is not equal to 0, then the matrix is non-singular, and then the system of equations are not linearly dependent, they are linearly independent. So we can see here also that here the first row and second row are dependent on each other, because the second row is scaled up by a factor 2, because 3 2s are 6, 2 2s are 4. So there is same scale, that is 2. So this was all about the determinants and the singularity. That means if the determinant is equal to 0, I will write again. I will now summarize this. If I have a matrix, that is, if the determinant of a matrix is equal to 0, implies matrix is singular. Now if matrix is singular, means there is linear dependence. There is linear dependence. That means system of equations have infinite solutions, or no solution is possible. We can say no solution is possible. Now if the determinant is not equal to 0, that means implies matrix is non-singular. Means there is linear here it is linear independence. See whatever. Now this means if there is linear independence, means we have a unique solution. Now determinant of a 2 cross 2, that is 2 by 2 square matrix, is called second order determinant. That is second order determinant. Now that means the determinant of a 2 by 2 matrix is called second order determinant. Similarly, if I have a matrix that is 3 by 3 matrix, and one important point is to be remembered, we only can find the determinant of a square matrix. So determinant, if we have to find the determinant, we can only find the determinant of a square matrix. A square matrix is a matrix where the number of rows are equal to the number of columns. Here the number of rows are 2 and the number of columns are 2. So this is to be remembered. And the determinant of a 3 by 3 matrix is called third order determinant. If we have a 3 by 3 matrix like here, 3 by 3 means where there are 3 rows and 3 columns. Now the determinant of a 3 by 3 matrix is called third order determinant. Now the symbol for determinant is this symbol. Now there are some steps to find the determinant of a 3 by 3 matrix. The first step is take the first element of the first row A11 and mentally delete the row and column in which it appears. Then multiply A11 by the determinant of the remaining elements. Now we take the first element of the first row, here it is A11, and we mentally delete the row and the column in which it appears. Then we multiply this A11 by the determinant of the remaining elements. Here the remaining elements are A22, A23, A32 and A33. So this is here the second order determinant. We have seen in earlier videos how to find the determinant of 2 by 2 matrix. Now our determinant will be like this. This is the symbol for determinant. This is equal to the first element, that is A11, and we multiply this first element by the determinant of these remaining elements, that is A22, A23, A32 and A33. So this was the first step. Now similarly we take the second element of the first row, that is we take this element. Here we will take this element. Now we take the second element of the first row and delete the row, that is we will delete this row and this column in which it appears. That is, take the second element of the first row, that is A12, and mentally delete the row and column in which it appears. We take this A11 and mentally delete the row and the column in which it appears. That is means we have then A12. So then multiply A12 by -1. So we will multiply this A12 by -1 times the determinant of the remaining elements. Now the remaining elements are here. Here the remaining elements are A21, A23, A31 and A33. So this was the second step. I repeat the second step. We take the second element of the first row and we mentally delete the row and the column in which it appears. Like this, we delete this row and this column. Then multiply this A12 by -1 times the determinant of the remaining elements. The remaining elements are this and this, plus plus we take the next step, that is similarly we take the third element of the first row a1 3, sorry it is here a1 3, that is we take the third element of the first row, that is a1 3. So I will circle this and mentally delete the row and the column in which it appears. So we take this element, that is a1 3, and mentally delete the row and the column in which appears. Then multiply this element by the determinant of the remaining elements, that is we multiply this by the remaining elements, determinant of the remaining elements, that is a21 a22 a31 and a32. Now we will solve this. This will become a11. Now this these two elements on the principal diagonals will be multiplied, that is a22 times a33, and we will subtract it by the non-principal diagonals, the product of the elements on the non-principal diagonals, that is these two, now these two elements, that is a32 times a23. Now here a12 times -1, so this will become minus, so I will write this here, this will become minus a12. Now similarly here we will multiply these two terms, that is a21 times a33. From this we will subtract the product of these two elements, that is a31 a23. Now it is here plus this a13, this a13. Now similarly multiplying these two elements on the principal diagonal, that is a21 times a32 minus the product of these two elements, that is a31 times a22. Now the number we will get when solving these, we will get a number that is scalar. Now we will get a number that is a scalar, or it is a number here. So this is how determinant is found of a 3 by 3 matrix. Now if I give an example, if I give an example, that is, let us rub this, or I put this out. Now if I have an example, let us say I take this red color marker here. So if I have a 3 by 3 matrix, that is, let us say this is 2 1 3, second is 4 2 1, and 3 6 5. So we will find the determinant of this matrix. Since it is a 3 by 3 matrix, we can find the determinant. In the earlier videos, as we have told, we can only find the determinant of a square matrix where the number of rows and number of columns are equal. Now the first step is, as we have seen, is in this example, what we do, we take this A means the determinant of this this matrix. Now we take the first element, that is this 2, and mentally delete the row and the column, that is we delete this row and this. Now we multiply this 2 by the determinant of the remaining elements. Here this is 2, 6, 1, 5. So I will write 2, 6, 1, 5. So this is the first step. Now second step is we take the second element, that is 4, and we multiply first it by -1, and then mentally delete the row. It is like this row, the row and the column in which it appears, that is these two. Now we multiply this by the determinant of the remaining elements. Here the remaining elements are 1, 3, 6, 5. So I will write 1, 3, 6, 5 plus I take the third element, that is 3, and mentally delete the row and the column in which it appears. So I will write here first 3 and multiply this 3 by the determinant of the remaining elements. The remaining elements are here 1, 2, 3, 1. So I will write 1, 2, 3, 1. Now solving this, here it is 2. Now multiplying these two diagonal elements, principal diagonal elements, that is 2 into 5. So this is 2 into 5 minus the product of these two elements, that is 1 into 6. Similarly here 4 into -1, that will become -4. Now multiplying these two elements first, that is 1 into 5, 1 into 5 minus this 3 into 6, 3 into 6. Similarly this is plus 3, this will become 1 into 1, that is 1 into 1, then elements in the product diagonal element minus 3 into 2, 3 into 2. Now further solving this will become 2. Now these 2 5s are 10 minus 1 6 are 6. This plus I will write this as -4. Now here it is 1 into 5 is 5, that is 5 minus 3 6 are 18, plus this 3. Now here it is 1 1s are 1 minus 3 2s are 6. So this will become 2. Now 10 minus 6 is that is 4, plus -4. Here 5 minus 18, 5 minus 18 is that is -13. Now this is plus 3. Now 1 minus 6 is -5. Now this will become 2 4s are 8, plus now -4 times -13, this will become plus 52. Now 3 into -5, that is -15. Now this 8 plus 52 is 60, minus 15, this will become 45. Now since A, the determinant of this matrix, is equal to 45, this means which is not equal to 0, implies A is non-singular. By non-singular means this determinant has a unique solution. If the value of A was 0, then this determinant would have no solution. So this was all about finding the determinant of 3 by 3 matrix. We will discuss about minors and cofactors. In earlier video, we have discussed about how to find the determinant of a 3 by 3 matrix. Now, the elements of a matrix remaining after the deletion process form a subdeterminant of matrix called minor. That is, the elements of the matrix remaining after the deletion process. In earlier video, I have explained the deletion process. Form a subdeterminant of a matrix called minor. That is, a minor, that is Mij written in these two lines, between these two lines written Mij, is a determinant of the submatrix formed by deleting ith row and jth column of the matrix. That is, a minor is denoted by this symbol. This Ij is the ith row, and this is the ith row, and this is the jth column. That is, the minor here will be, if this is the given matrices, then the first minor will be m of 1 1. That is, the first minor is equal to, we will delete the first row and the first column here, that is ith row and jth column. So the remaining sub matrix is A 2 2, A 2 3, A 3 2, and A 3 3. So this is a minor. Similarly, the second minor here is M12, M12. So here we will delete this first row and second column, and the elements here are then A21, A23, A31, and A33. Similarly, the third minor is, that is M13. Then this third minor is, that is deleting the first row and the third column. Then the remaining elements are A21, A22, A31, and A32. So here this M11 or M12 or M13, these are the minors of A11, A12, A13, these small a1. That is, I will write here this this M11 is, this M11 is here, the minor is denoted by these two lines also. So I will put this is the symbol for minor. Here it is also. So this is the symbol for minor. Now therefore M11 is minor of this element, that is A11. Similarly, M12 is minor of this element, that is A12, this second element, A12. Similarly, M13 is minor of this third element, that is A13. Now the determinant can be written as, we can write the determinant like this is the symbol for determinant, can be written as, that is A11 multiplying this by the first minor, that is m11 plus a12, multiplying this by -1. We have seen in the earlier videos. So it is to be multiplied by -1 times the determinant, the second minor, that is m12. Similarly, this third element, that is a13 plus a13, and multiplying this by this third minor, that is m13. So this is how we write the determinant. We can write the determinant like this also. Now this a cofactor, this cofactor is, I will write the definition. So first I will erase this. Now a cofactor that is denoted by Cij is a minor. This is also a minor with a prescribed sign. That is, a cofactor is a minor. So this is also a minor, but there is a definite sign given, or a prescribed sign given. The rule for sign of a cofactor is, that is, if this is Cij is the this is the cofactor, then the sign of this cofactor is given by, that is given by -1 raised to the power I plus j. Now this I is the ith row and j is the jth column. Thus, if I plus j, this subscript, the sum of the subscript is even number, then Cij will be equal to this minor, that is Mij. That is, if I plus j is an even number, this is an even number, this means this Cij, that is a cofactor, is equal to the minor. So that is minor, which is denoted by, which we have seen, Mij. Then if the sum of the subscripts is an even number, then Cij is equal to Mij, because -1 raised to the power even, raised to an even power, is positive. That is always positive. So we can say there is no difference between a cofactor and a minor when the sum of the subscripts, superscripts, that is ith row and jth column, the sum of these two numbers is even number, then there is no difference between minor and a cofactor. Now if I plus j, if it is an even, if the sum of these is odd, then this Cij is equal to -1 times the Mij. That is, this cofactor is equal to -1 times the minor, because -1 raised to the odd power is always odd. That is where this -1 came from. So we will take an example here. Now let's have an example on minors and cofactors. If we are given a matrix that is A is equal to A11, A12, A13, A21, A22, A23 and so on, these are the elements of this matrix A. Then the first minor, which is denoted by this M11. Now this M11 is the minor at the place of A11, that is the minor of the first element, that is this is given by we mentally delete the row and the column in which the first element, this A11, appears and take the determinant of the remaining elements, that is A22, A23, A32 and A33. So this is the minor M11 in place of this element A11. Similarly, the second minor is denoted by M12. So this M12 is a minor in place of this element A12. Now the minor at this place is found by we mentally delete the row and the column in which this element appears and take the determinant of the remaining elements. Now if we delete this row and this column, we are with these four elements, that is A21, A23 and A31, A31 and A33. Now this is the M12 is a minor in place of this A12. Similarly, the third minor will be, that is M13. Now the third minor is found by mentally deleting the row and the column in which this A13 appears and take the determinant of the remaining elements. The remaining elements are then A21, A22, A31 and A32. So the third minor will be A21, A21, A22, A22, A31, A31 and A32. Similarly, the fourth minor is the minor in place of this A12 element is, so I will write here that M12. The minor at this place is this place, that is A12. We mentally delete the row and the column in which this element appears and take determinant of the remaining elements. The remaining elements are A12, A13. So I will write here A12, A13, this row and this column. So we have then A32, A32 and A33. So accordingly we can find the minor at place of A22, A23 by mentally deleting the row and the column in which the corresponding element appears and take the determinant of the remaining elements. Now the cofactor is a minor with proper sign, that is the cofactor at first minor is given by, that is the cofactor C11 is given by we take -1 and raise it to the power of the addition of the subscripts, that is 1 plus 1, and multiply this by this M11, that is M11. So giving a minor a proper sign forms the cofactor. So here in this case, -1 raised to the power 1 plus 1 is 2. So the -1 raised power 2 is +1. So the first cofactor have the same sign as that of the first minor. Similarly, the second cofactor, this C12. Now the second cofactor has the sign, the general formula is -1 raised to the power of the addition of the subscripts, that is 1 plus 2, and multiply it by the second minor. The second minor is M12. So minus 1 raised to the power 3 will be minus 1. So here the second minor will be negative, that is equal to minus times m1 2. Similarly, the third cofactor is given by c1 3, and the formula is we take minus 1 and raise it to the power of the addition of the subscripts, that is 1 plus 3, and multiply it with the given minor. Now the given minor is here m1 3, so I will write m1 3. So here 3 plus 1 is 4, minus 1 raised to the power 4 is plus 1, because minus 1 raised to the power of an even number is positive, and minus 1 raised to an odd power is minus 1. So here this is m1 3. So the first cofactor is, that is c, here the first cofactor is here c11, this will be the positive one. The first minor was our so I will write here a22, a23, a32 and a33. Similarly, here the second cofactor c12 is equal to, now the second cofactor is, and the sign of the second cofactor is minus, as we have seen here. So this will be equal to minus times a21, a23, a31 and a33. Similarly, the third cofactor c13, which we have, the sign of the third cofactor is, here we have seen this is positive, and our minor at that place was this a21, a21, a22, a31 and a32. So accordingly we can find the sign of the minor. So the general formula is the cofactor, the sign of the sign of the cofactor is, if we are given Cij, means the cofactor at ith row and jth column is equal to minus 1 raised to the power of the addition of the subscripts, that is I plus j, and multiplying it with the minor at that the corresponding minor, that is mij. So if I plus j is, if I plus j is even, then sign of cofactor is, positive. Therefore sign is positive, and if I plus j is odd, then sign of cofactor is negative. Why? Because minus 1 raised to an even power is always plus 1, and minus 1 raised to an odd power is minus 1. Here we can see, if I have minus 1 raised to any even power, that is 2, so this will become plus 1, and minus 1 raised to an odd power, let us say 5, so this will become minus 1. So this was now let's have a specific example on the minors and cofactors. That is, find the first part is minors and the B part is cofactors for the elements of the first row. The question tells us to find the minors and cofactors for the first row. So the solution would be like this. That is, to find the minor, first finding the minor, this is the A part. Now the first minor here, that is denoted by M11, the first minor, that is the minor at this place, at the first place is, we mentally delete the row and the column in which the first element appears and take determinant of the remaining elements. The remaining elements are these four elements. So this is -3, 2, 7, 4. Now solving this, now this is -3 into 4, that is multiplying these two elements, and from there subtracting the product of these two elements. This is 2 and 2 multiplying it with 7. So this is 3 4s are 12 minus 12, and here it is -14. So now this is equal to -12 and -14 is, that is -26. This is the first minor. Now the minor at this position, that is at the second element, is, that is denoted by M12. Now what we will do, we will mentally delete the row and the column in which the second element appears and take determinant of the remaining elements. The remaining elements are here 6, 1, 7, 4. So I will write here 6, 1 and 7, 4. Now solving this, now this is 6 into 4 and minus 1 into 7. So this is 24 minus 7, that is equal to 7, that is equal to 17. So similarly the minor at the third place is, that is M13, that is equal to, now mentally deleting the row and the column in which the third element appears, take the determinant of remaining element. So this is 6, 1 minus 3, 2. So I will write 6, 1 minus 3 and 2. Now solving this, this is 6 into 2, 6 into 2 minus 1 into minus 3, that is 1 into minus 3. So this is equal to 12. Now minus is plus, now this is plus 3. So here it is 12 plus 3 is 15. So these are the minors for the first row. Similarly we can find the minor for here, that is it is M11, M12, M13. Now here it is M21. So M21 is equal to, we mentally delete the row and the column in which this element appears and take the determinant of remaining elements. The remaining elements are 2, 2, minus 4 and 4. So 2, 2, minus 4 and 4. Now solving this, this is 2 into 4 minus 2 into minus 4. So this is 8. Now minus is plus, this is plus 8, this is 16. Similarly we can find the minor here, M22, M23 and so on. Now you can calculate others, because we were told to find the minors along first row. We have completed. This is, these three elements are on the first row. Now the B part is to find the cofactor. Now cofactor at this place is equal to, this is denoted by C11. Now cofactor is simply a minor along a proper sign. That is, here we write first minor, that's M11, and multiply it with -1 raised to the power of the addition of the subscripts, that is 1 plus 1. So this is equal to -1 square, that is -1 square times M11. So this is now -1 square is plus 1. So here the sign is positive, so I will write M11. So this is the first cofactor. Similarly the second cofactor is C12. Now this is equal to -1 raised to the addition of the subscripts, that is 1 plus 2 and the minor at that place, that is M12. Now here this is -1. Now this is 2 plus 1 is 3, M12, that is equal to now -1 raised to an odd power is minus, so -1 is minus, multiplying it with M12. So the cofactor here is m11, which we have calculated, that is minus 26. So there is no change in the sign. Here it is 17, m12, sorry, I will write here 17, that is 17, and here the sign is minus. So the cofactor C12, the sign is minus 17, and here we can see minor was plus 17 and it is minus 17. Now similarly, the third cofactor, that is C13, is equal to minus 1 raised to the power of the addition of subscripts, that is 1 plus 3, and multiply it with the corresponding minor. So that is m13. So this is equal to minus 1. Now 3 plus 1 is 4, m13. Now minus 1 raised to an even power is positive, that is here m13. Now our m13 here is 15. So this is 15. So there is no change in the sign. Similarly, the cofactor for C21, that is the cofactor at this place. This is also equal to minus 1 raised to the power of subscript, that is 2 plus 1, this, and multiply it with the corresponding minor, that is m21. Now this is minus 1 raised to the power, that is 2 plus 1 is 3. So, and multiplying it with the corresponding minor, that is m21. Now minus 1 raised to an even odd power is minus, so this is minus m21. Now our m21 was 16. Now the sign here is minus, so this is minus. And similarly, we can form a cofactor matrix. The cofactor matrix will look like this. So I will rub this. I should rub. Where should I write this? So I will rub this out. Now the cofactor matrix would look like this. The elements in the cofactor matrix will be, the first is C11, second is C12, third is C13, similarly C21, C22, and C23. This is equal to, if this is the cofactor matrix. If C denotes the cofactor matrix, then C is equal to, now the first cofactor was, the element is minus 26. Now here it is minus 17, and here it is 15. Then we have minus 16, and similarly we can find the other cofactors, because the question tells us to find the minors and cofactors for the elements of the first row. So we have calculated only those. In addition, we have calculated the minor for this element and its corresponding cofactor. Now we will see the cofactor matrix and adjoint matrix. Now a cofactor matrix is a matrix in which every element Aij is replaced with cofactor Cij. That is, if we are given a general matrix like this, now if every element of this matrix is replaced with the cofactor, then we say the matrix formed by the cofactors is a cofactor matrix. That is, this A11 is replaced with this cofactor, that is C11. Now how it is formed? We see here A11, the position of A11, and we mentally delete the row and the column in which it appears, and we get these elements. Now the determinant of these elements is denoted by C11. That is, this C11 is here. This is the determinant of A22, A22, A23, A32, and A33. Similarly, this A12 is replaced with it is cofactor, that is C12. Now the cofactor of A12 here is we mentally delete the row and the column in which this element appears and form a new subdeterminant of the remaining elements. Now if we delete this row and this column, we are with this element 1, 2, 3 and 4. That is the cofactor of this C12 is, that is A21, A23, similarly A31, this element, and A33. Now similar is case with this when we replace A12 with its cofactor, that is C13. Now if we delete the row and the column in which this element appears, the remaining elements form a new subdeterminant, that is these 4 elements. Now the cofactor of this C13 is, so for the sake of understanding I will show you. Now this column and this row is deleted and we are with these 4 elements, that is A21, A22, A31 and A32. Similarly, we replace every element of this matrix with its cofactor. This process goes on up to we find out all the 9 cofactors. Let us I take the random another cofactor. Now if it is the element A23, now we have to replace it with the cofactor, that is C23. Now here the cofactor will be, we will delete the row, this row and the column in which it appears. Now we form the matrix of the remaining elements. Now the remaining is this and this. Because we delete this row, we delete here this row and this column, the remaining elements will form another cofactor, that is C23 is here, A11, A12, A11, A12 and A31 and A32, A31 and A32. Now I will not show the all 9 cofactors. You can check it out easily here. Similarly, if we have A31, we have to delete the row and the column in which appears and take the determinant of the remaining elements. So accordingly we will get the 9 cofactors here. Now the matrix formed by these cofactors is called the cofactor matrix. Now in parallel I will give an example. If I have a matrix that is A is equal to 1, 2, 3, 1, let us say this is 4, 6, 8, 2, 3, 5. Now the cofactor of this will be, this matrix will be, that is C is equal to, now we will replace every element here with its cofactors. Now the cofactor of this first element is, we delete the row and the column in which it appears and take the subdeterminant of the remaining elements, that is 6, 8, 3, 5. So the first cofactor will be 6, 8, 3, 5. So this is the first cofactor. Similarly, for 2 we delete the row and the column in which appears and take the determinant of the remaining elements. Here this is 4, 2 and 8, 5. So the second cofactor is that is we have deleted this row and this column, that is 4, 2, 8, 5. So I will write 4, 2, 8, 5. Similarly I will take the third element and replace it with its cofactor. that is I will delete the first row, the row in which it appears, and the column in which it appears mentally. So I take the determinant of the remaining elements, that is 4, 2, 6, 3. So this will become 4, 2, 6, 3. Having done this with the first row, similarly we take the second row. Now 4 appears in the first column, that is the first column and second row. So I will delete this column and this row and take the determinant of the remaining elements, that is 2, 3, 3, 5. So I will write here 2, 3, 3, 5. Similarly here 6, I will delete the row and the column in which it appears, that is this row and this column. Now the remaining elements are 1, 3, 2, 5. So I will write here 1, 3, 2, 5. Similarly 8 is in this row and this column, that is this and this, that is 1, 2, 2, 3 will be the cofactor, that is 1, 2, 2, 3. Similarly this 2 appears in the third row and first column, and we mentally delete these 2 rows and columns in which 2 appears and take the determinant of the remaining elements. Here it is 2, 6, 3, 8. So I will write here 2, 6, 3, 8. Now similarly here 3 appears in the third row and second column. I delete third row and second column, third row and second column, and take the determinant of the remaining elements. Here it is 1, 4, 3, 8. So I will write here 1, 4, 3, 8. Similarly the last element is 5. It appears in the third row, third column. So I will delete these this row and column. Now I will get 1, 2, 4, 6. So I will write here this is 1, 2, 4, 6. Now this matrix is called the cofactor matrix of the given matrix. Now an adjoint matrix is the transpose of the cofactor matrix. Now one thing is to be remembered here, we have to change the signs alternatively here. We have to change the signs alternative here, because according to the law of cofactors, this first element will be positive and second will be negative. This will be positive, third will be negative. This is positive, this is negative, this is positive, this is negative, and this is positive. Why? Because it is, we see here, if A12 is the element, if this is the element, this 2, it is at a position that is A12. Now the sign of this cofactor, that is the second cofactor, is equal to, that is -1 raised to the power of the subscripts, that is 1 plus 2. Here we see this is -1 raised power 3. Now -1 raised to an odd power gives us -1. Similarly, if I have the third element, that is this, the position of this element is this 3 is at so I will write here this 3 is at A13. Now the sign is given by -1 raised to the power of the subscripts here. Now the subscript is here 1 plus 3, so I will write 1 plus 3. So this is -1 raised power 4. Now minus raised to an even number gives us +1. Therefore I have written here it is positive. Similarly, this element here, this 4, it appears at A21. The address of this element is A21. That is A21. 2 1. Now the sign of the cofactor, corresponding cofactor of this element is, that is equal to -1. This is the general formula. We add this subscripts and raise these subscripts to the power, to the exponent of -1. That is, here this is 2 plus 1. Now here it is -1 raised power 3. So the sign will be here, because minus power raised to an even number, odd number gives us -1. So here I have written this minus sign. Now similarly, if this is the element, the address of this element is A33. That is third row and third column. Now the sign is here positive. We will see why. That is A33. Now to get a sign, we take the -1 and raise it to the power of the addition of the subscripts. That is 3 plus 3. Now 3 plus 3 is 6. That is -1 raised power 6. Now -1 raised to an even is +1. Here we can see this is the positive here. This cofactor is positive. So the general rule is -1 raised to an odd power is -1, and -1 raised to an even power is 1. And we know from the earlier video that cofactor is a minor. That is, cofactor is a minor with proper sign. That is, the difference between minor and the cofactor is of the sign. That is, cofactor is usually with its sign. The sign of the cofactor depends upon the element, the position of the element. That is, the row number and the column number, as we have seen in these examples. Now this was all about the cofactor matrix. Now the adjoint. So I will rub this out. We will see the adjoint matrix. Transpose of cofactor matrix is called the adjoint matrix. So I will write, if A is a general matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now if A is the general matrix, now the cofactor of this element is, and this matrix is, that is given by the C11, C12, C13. That is the adjoint matrix. C21, C22, C23. Similarly, C31, C32, and C33. Now this is the cofactor matrix. Now the adjoint of the cofactor matrix gives us the transpose of the cofactor matrix gives us the adjoint matrix. Now the transpose of this matrix, this cofactor matrix, that is C dash, means the transpose of this matrix, this adjoint matrix, that is equal to, we will replace the row with the column. So this row will become column. So this will become here C11, C12, C13. Similarly, this will become C21, C22, and C23. Similarly, this row will become the column, that is C31, C32 and C33. So therefore adjoint, which is denoted by this adjoint A of A, is equal to the transpose of C. So this is the adjoint matrix. This is the adjoint matrix. Adjoint matrix. Now we will give an example on the adjoint matrix. So for that I will rub this here. Let us take an example. If I have a general matrix, that is, or I have a matrix like this: 1 2 3 2 1 0 4 5 2. If this is a matrix, now the adjoint of this matrix, as we have seen, is given by, so I will write here, that is C is equal to, so I will write here, I will write the cofactor matrix here. That is, the cofactor of the first element is this row, this column, 1 5 0 2. So I will write 1 5 0 2. Similarly, the 2 is here, delete this row and the column, we get 2 4 0 2. That is 2 4 0 2. Similarly, the third one is, the cofactor of this element is, delete the row and the column in which appears. Now the remaining elements are 2 4 1 5. So I will write 2 4 1 5. Similarly, here this is 2, delete the row and the column in which it appears, we get 2 5 3 2. That is 2 5 3 2. Similarly, 1, delete the row and the column, we get 1 4 3 2. So that is 1 4 3 2. Similarly, delete the row and the column. Now row and column, we get 1 4 2 5. We get 1 4 2 5. Similarly, this 4, we delete the row and the column, we get 2 1 3 0. So 2 1 3 0. Similarly, this 5 appears in this row and this column, we get 1 2 3 0. So here it is 1 2 3 0. Similarly, we have this 2 here. Now delete the row and the column in which it appears, we get 1 2 2 1. That is 1 2 2 1. Now we have to give the proper sign. We have seen the sign changes alternatively. First is positive, second is negative, third is positive, fourth is negative, fifth is positive, sixth is negative. Similarly, this is positive, this is negative, and last one is positive, because a cofactor is a minor with proper sign, and sign is given by the address, the subscript of the address, and that is raised, that is equal to the I plus j, and that is sign is given by -1 raised to the power of the addition of the matrix in which the element appears. Here we can see this is A13, this is A13 here, this is 1, A13 is equal to, now we will add the subscripts here, that is 1 plus 3, that is -1 raised power 4, that since -1 raised to the even number is A1, that is plus 1. Here it is plus, here it is minus, because of the law of the cofactors. Okay, I have shown in the previous example how it is done. Now this is the cofactor matrix, and I have given the proper sign to these. Now solving further this will become here. Now 1 into 2, 1 2s are 2, minus 5 zeros are 0. So we will get 2 minus, should I elaborate this here? I should elaborate this. Now because of the lack of the space, I will try to make it smaller here. Now this is 1 into 2, that is 2. 2 minus 5 into 0, that is 0. Similarly here the sign is minus, so I will write here minus. Now here it is 2 2s are 4, 4 minus 4 zeros are 0. Similarly here this is 2 5s are 10, that is 10, minus 4 1s are 4. Similarly here the sign is minus because of the law of the cofactors. Here 2 2s are 4, 4 minus 5 3s are 15. Similarly here the element will be 2 1s are 2, minus 4 3s are 12. Here we have the minus. Now 1 5s are 5, minus 4 2s are 8. Similarly here this is 2 zeros are 0, this is 2 zeros are 0, minus 3 1s are 3. Here it is minus is with it, that is 1 zeros are 0, minus 2 3s are 6. Similarly here it is positive, so 1 1s are 1, minus 2 2s are 4. Now the matrix we got is, that is, this is 2. Now here it is minus 4. Here 10 minus 4 is 6. Now yes, it is 6 here, obviously. Now 4 minus 15 is 4 minus 15 is minus 11. Now we have another minus, so this will become plus 11. Similarly 2 minus 12 is minus 10. Here 5 minus 8 is minus 3, and we have another minus in multiplication, so this will become plus 3. 0 minus 3 is minus 3. Now this will become plus 6, and here it is minus 3. So this matrix, so this is the cofactor matrix of the given matrix. Now implies, I will write here, this is the cofactor matrix. This is the cofactor matrix of the given matrix. Now the transpose of this matrix gives us the adjoint matrix. That is, adjoint matrix is given by the transpose of the cofactor matrix. Now the cofactor matrix is here. This is the cofactor matrix. Now transpose means interchanging rows with column. So I will write here, transpose in matrix means interchanging rows with columns. Now this is the row, and I will replace it with column. So if here it is row, I will make it column. So this is 2 minus 4 6, I will make it column, that is 2 minus 4 and 6. Similarly I have, this is row here, 11 minus 10 3, this will become column, that is 11 minus 10 and 3. Similarly here it is minus 3 6 and minus 3, it is row, and I will make it here column. So minus 3 6 and minus 3. So this is the cofactor, this is the adjoint of the given matrix. Now I repeat quickly, if A was given us a matrix, then first we found the cofactor matrix. After that, to find the adjoint matrix, we transpose the cofactor matrix. That is, we transpose this matrix. The resulting matrix will be the adjoint matrix. So this was all about the cofactor matrix and adjoint matrix. We will learn about the inverse matrices. Now an inverse, which is denoted by this symbol a to the power minus 1, can be found only for a square non-singular matrix. A is a unique matrix satisfying the relationship which I will give here. Now first of all, square matrix can be found only for a square matrix. By square matrix we mean the number of rows are equal to the number of columns. That is, if I have a matrix like this, 1 2 4 3. This is a square matrix of order 2, which is denoted by 2 by 2. Now we can find inverse for only for a square matrix, and another example could be 1 4 3 2 6 1 1 0. Let us say it is 2. Now this is also a square matrix of order 3 by 3. So we can find an inverse only for a square matrix. That is, the matrix, the square matrix should be also non-singular matrix. The matrix should be also the non-singular. By non-singular we mean that the determinant of the given square matrix must not equal to 0. That is, determinant should not be equal to 0. So these are the two conditions. First, the matrix must be the square matrix. Square matrix means the number of rows and columns must be equal. Second is the determinant must not equal to 0. The determinant we have shown in the earlier videos how to find the determinant, and in the subsequent examples we will see how to find the determinant. Now the relationship is given by, that is, the given matrix multiplying this with the inverse gives us the identity matrix. Now an identity matrix is a matrix where there are only ones in the principal diagonal and zeros everywhere else, is equal to the A inverse multiplied with the given matrix. Now the identity matrix is like, if I have 1 0 0 1, this is called the principal diagonal. The numbers, the elements on the principal that is principal diagonal must be only ones, and elsewhere must be 0. Like if I have another one, 1 0 0 0 1 0 0 0 1. So this is a identity matrix here. That is, multiplying the given matrix by its inverse gives us the identity matrix, or multiplying an inverse by its by the given matrix gives us the identity matrix. Now how to find the inverse? Now the formula for finding inverse is, that is, inverse of a matrix is equal to 1 divided by the determinant of the given matrix multiplying this by adjoint of the matrix. So this is the formula for finding the inverse of the matrix. Now we will see an example. For that I have to rub this portion. So this inverse matrix or anything like this is used in mathematical economics. Now in the subsequent videos we will see the Cramer's rule, others input output problems. Now first concentrating on finding the inverse. Now let's take the marker. Now if I have an example like, first I will see whether it, now it is too much written here on this. Now it is okay here. Now if I have a matrix, let us say A is equal to 1 0 5 2 1 6 3, let us say it is 4 and 0. Now if it is a given matrix and I have to find the inverse of this matrix. Now first condition is that the given matrix must be a square matrix. Here this is a first condition is it should be square. It should be a square matrix, which is the case here because the number of rows are 3 and number of columns are 3. So the rows and the columns are equal here. Second condition is, so there it is 3 cross 3, number of rows are equal to number of columns first. Second condition is that the determinant of the given matrix must not equal to 1, that is, must not equal to 0. that is determinant should not be equal to 0, implies it must be a non-singular matrix. Matrix, that is we can find inverse only to a non-singular matrix. Now here we can see, now the determinant here is given by, we take the first element, that is 1, and multiply it with the given determinant. We delete the row and the column in which it appears, this one mentally, and multiply this determinant, that is here, that is 1 zeros are 0 minus 6 fours are, that is 24. Now this is minus sign which comes from the rule of the cofactors, which we have seen in the earlier videos. This is first is positive, negative, positive. Now here it is minus 2. Now this minus 2 row, delete the row and the column and take the determinant. Here it is 0 into 0, that is 0 zeros are 0, so I will write here 0 minus 5 fours are 20, so I will write here 20. Now plus this 3. Now delete mentally the row and the column in which the 3 appears, then we have this. Now the determinant here is 0 6 are 0 minus 5 1 are 5. Now solving this will give us, now here it is minus 24 times 1, that is minus 24. Now here minus 2 into minus 20 is plus 40, and here minus 5 times 3 is minus 15. Now minus 24 and minus 15, that is 5 plus 4, that is 9, and 2 plus 1 is 3, minus 39 plus 40, that is equal to 1. Here the determinant is equal to 1, that is which is not equal to here 0, implies we can find the inverse, that is we can find the inverse. Therefore inverse exists. Now to find the inverse, we form a cofactor matrix of this A. Now the cofactor matrix is, as we have seen, is given by, so I will repeat the rules here also. Now first element, we take the first element here, that is 1, and delete the row and the column in which appears, and take the determinant of the remaining elements. This will become the first cofactor, that is 1 4 6 0. So I will write 1 4 6 0. This is the first cofactor. Similarly, the first cofactor is positive, second is negative. Now second cofactor will be, now here it is 2, delete the row and the column in which appears, we get 0 5 4 0. So I will write 0, that is this, and this 0 5 4 0. So I will write here 0 5 4 0. Similarly, take the third element, delete the row and the corresponding column, we get 0 5 1 6, that is 0, but we have deleted this and this, 0 5 1 6. Similarly, take this element and delete the corresponding row and the column, we get 2 6 3 0. So here it is 2 6 3 0. Similarly, this one, delete the row and the column, we get 1 5 3 0, that is 1 5 3 0. Similarly, take this 4 and delete the row and the column in which it appears, this row and this column, we get 1 5 2 6. So here it is 1 5 2 6. Similarly, this 5, delete the row and the column, we get 2 1 3 4. So here is 2 1 3 4. Similarly, this 6, delete the row, the column, we get 1 0 3 4. So we get 1 0 3 4 here. Now the last one is 0. Now delete the row and the column, we get 1 0 2 1. That is 1 0 2 1 here. Now to check this out, to see whether I have done it properly here, I have some confusion. Here it is 5. I have deleted the row and the column. So here it is 2 1 3 4. 2 1 3 4. Okay. All set up to this. This is the cofactor matrix. Now first is positive, second is negative, third is positive, fourth is negative. That is alternative. We change the sign. Positive, this is negative, this is positive, this is negative. Now multiplying this, this is 1 zeros are 0 minus should I write it here, that is 0 minus 24. So we will get here minus 24. Here 0 5 fours are 20, that is minus 20, because sign is minus, that is minus 20. Similarly, 0 into 6 is 0, minus 5 ones are 5, that is minus 5. Here 2 zeros are 0, 6 threes are 18, that is minus 18, because of the given sign, minus 18. Similarly, 1 zeros are 0, minus 5 threes are 15, so 0 minus 15 is minus 15. Similarly, here we have 1 6 are 6, 6 minus 5 twos are 10, 6 minus 10 gives us 6 minus 10 gives us minus 4, but we have here positive, so this will become positive 4. Minus minus is plus. Here 2 4s are 8, minus 3 1s are 3, 8 minus 4, that is 5. Similarly, here 1 4s are 4, minus 3 zeros are 0, that is here minus 4. And here 1 zeros are 1 1s are 1, minus 2 zeros are 0, so we will get here 1. I hope the calculation is going right. Now this is C, implies C, this is the cofactor is minus 24, minus 20, minus 5, minus 18, minus 15, and 4, and 5, minus 4, and 1. Now adjoint is given. Now here we will see the transpose of this is C dash, means interchanging rows with columns. That is, row is interchanged with column. If it is here row, it will become column. So I will write minus 24, minus 20, and minus 5. And here minus 18, minus 15, 4, minus 18, minus 15, and 4. Similarly, 5 minus 4 1, 5 minus 4 and 1. So this is the transpose or the adjoint matrix. Now adjoint is given as ADJ, A is equal to the transpose of C, that is transpose which we got here, which is minus 24, minus 18, and 5, minus 20, minus 15, minus 4, minus 5, 4, and 1. Now the inverse is given by, we know what we are actually finding, that is a to the power minus, that means inverse is equal to the 1 divided by the determinant and a dj a, that is the determinant is 1 divided by the determinant we got, that is 1 here. Now multiply this with the adjoint which we got here, this matrix, that is minus 24, minus 18, 5, minus 20, minus 15, and minus 4, minus 5, 4, 1. So this will become now multiplying each element with the determinant. Here the determinant is 1, so this will become minus 24 divided by 1, that is minus 18 divided by 1, 5 divided by 1. Similarly, minus 20 divided by 1, minus 15 divided by 1, minus 4 divided by 1. Similarly, we have minus 5 divided by 1, 4 divided by 1, and 1 divided by 1. Because we are dividing here, the determinant was 1, so this will become this adjoint matrix also. If the determinant was 2, so this would have been 24 divided by 2, that is minus 12 here. But this is not the case. Here we are dividing with 1 because our determinant was 1. So this is minus 24, minus 18 and 5, minus 20, minus 15 and minus 4, minus 5, 4 and 1. Now to check whether we got the same, we got the result correctly, we have to multiply the given matrix by its inverse. If we got an identity matrix, then the result is correct. If not, then there is some mistake. So this is how the inverse is found. So I will repeat here. If A was given this, A is the given matrix. First of all, we have to check whether it is a square matrix. If it is a square matrix, then we can proceed to find the inverse. Since the number of rows and columns are equal, this is a square matrix. The second condition was that the determinant of the given matrix must not equal to 0. That is, determinant should not be equal to 0. That is, the given matrix must be non-singular matrix. A matrix where the determinant is non-zero is a non-singular matrix. Here both the conditions are satisfied because first it is square matrix. Similarly, determinant is 1, which is not equal to 0, so inverse exists. Now to find the inverse, we take the cofactor matrix of the given matrix. Now the cofactor matrix is formed by replacing each element of the given matrix by its cofactor. That is, if this is first element, we mentally delete the row and the column in which it appears and take the determinant of the remaining elements, which are here 1, 6, 4, 0. Similarly, we found all the cofactors here, and with that we give them the proper sign. First is positive, second is negative, positive, negative, positive, negative, positive, negative, and positive. Now this rule is given by, that is to find the sign of the cofactor matrix in a matrix is given by the position of the matrix, that is A, I, J. To see the sign, we take this I and J, I plus J, we add the I and J and make it the exponent of the minus 1. Now if I have A31, now here A31 is this element, third row and first column. Now the sign here will be, then the sign of this element is given by minus 1 raised to this subscript, that is 3 plus 1, that is minus 1 raised to the power 4. Here it is, since it is even here, minus 1 raised to an even power gives us 1. That is, here the sign is positive. Similarly, if I have to find the sign of this element here of the cofactor matrix, then here it is at the position, that is 3, 2, that is third row and second column. So here the sign will be, that is A32 is equal to minus 1 raised power 3 plus 2, 3 plus 2, which is equal to minus 1 raised power 5. Now minus 1 raised to an odd power gives us the minus 1. Here we have seen the sign is minus. Similar is the case with every element. Now first we find the cofactor matrix. After that, which is after manipulating or solving this, we get this matrix. Now we take the transpose of the given cofactor matrix. Transpose of a matrix is interchanging the rows with the columns. Here the row, it is row, and this will become column. Now after that, the adjoint is given as the transpose of the cofactor matrix, which is this was the transpose matrix, transpose of the cofactor matrix. So this is the adjoint matrix. That is, adjoint matrix is the transpose of the cofactor matrix. Now inverse is given as 1 divided by the determinant multiplying this by the adjoint A. That is 1 divided by the determinant is here 1, and multiplying this with this adjoint A. Now after dividing, we got this minus 24, minus 18, 5, and so on. This is the method how to find the inverse of a matrix. I hope. Now the Cramer's rule states that xi is equal to the determinant of ai divided by the determinant of a, where this xi is the ith unknown variable in a series of equations, and this determinant, this a, is the determinant of the coefficient matrix, and this ai is the determinant of the special matrix formed from the original matrix by replacing the column of coefficients of xi with column vector of constants. That is, if we have an example, it will be clear to you what is the meaning of this ai, this a, and this xi. If I have an example, let us say I have a system of linear equations like 6x1 plus 5x2 is equal to 49, and another one is 3x1 plus 4x2 is equal to 32. If I have this system of linear equations, first of all, the first step is to express these system of equations in matrix form. So we will express these in matrix form. That is, the matrix form is A x is equal to b, where this A is coefficient matrix, and this x is the solution vector, and this b is vector of constants, Now we will express the first part. The first step is to express the given system of linear equations in a matrix form. That is, for the first one is a coefficient matrix. So I will write here the coefficient of x1 is 6, and the coefficient of in the second equation, that is 3. Similarly, the coefficient of x2 is 5, and the coefficient of x2 in second equation is 4. So this is our A. Now this x is the solution vector, that is the variable vector x1 and x2. Now this is equal to this b, the vector of constants, that is 49 and 32. So I will write 49 and 32. So this was the first step. Now second step is to find the determinant of this matrix, which is A. Now the determinant find, so I will write here find determinant. That is A, determinant of A. I will write here the determinant is that A is this determinant A is equal to, now the determinant of this is now 6 into 4 minus 3 into 5, that is 6 into 4 minus 3 into 5. That is first multiplying the elements on the principal diagonal and subtracting from it the elements of non-principal diagonal, that is 3 and 5. So this is 6 4s are 24 minus 3 5s are 15. Now this comes out to be 9. So this was the first step. First step was to express the system of equations in matrix form and find the determinant of this matrix, the coefficient matrix, which is A. Now the second step is solve for x1. Now to solve for x1, that is to solve for x1, that is to solve for this variable, replace column first, that is this column first, that is the coefficient, the coefficient of x1 with the column of constant, with the vector of constants, that is B, and forming a new matrix A1. That is to solve for x1, replace the column first. We replace this column first with the vector of constants. That is, we replace this column with this column. So in place of 6 3, we write 49 and 32 and form this new matrix and name it A1. That is, our A1 is our new matrix is, that is A1, which is the new matrix, that is replacing these elements, the coefficients of x1 with the constant vector, that is vector of constants. So in place of 6 3, I will write 49 32, and this will remain same, 5 4. So this is our A1. Now we will find the determinant of this A1, that is find determinant of A1. Now the determinant of A1 is now this is 49 into 4 minus 32 into 5, so this is 4 9s are 36, 4 4s are 16, 17 18 19. So this is 196 minus 4 9, here 5 4s are 20 and 5 3s are 15, 16 17 16, sorry. So this is 196 minus 160, that is 36. So our determinant A1 is 36, and we will use the Cramer's formula for finding the x1. Therefore, using Cramer's rule, that is x1, that is the value of the x1 is equal to this determinant, here it is A1, this special determinant, dividing with the coefficient matrix determinant, which we have calculated here, that is 9. So dividing this by this determinant, Now the determinant of the new matrix was, that is 36, and the determinant of the coefficient matrix, the original matrix, was 9. So this will give us 9 ones are 9, 6s are 9 fours are, that is 9 ones are 9 fours are. So the value of x1 is 4, x1 is 4. Now similarly we have to solve for x2, that is the next step is to solve for x2. We will go by the same steps except for the x1s. We have the x2, that is to solve for x2, to solve for x2 replace column 2 of x2s, that is the coefficients, whatever this is the spelling. I'm somewhat weak in the spelling, so coefficient of x2 from original matrix, original matrix with the column vector, that is with the column vector of constants b. Now this will forming a new matrix, that is A2, that is A2 is equal to that. This new A2 is, we have to replace the column second of the original matrix with the vector of constants. So in place of 5 4 we have 49 32. So our new matrix will be 6 3 and 49 and 32. Now we have to find the determinant of this A2, that is the determinant of A2 is equal to 6 into 32 multiplying the principal elements on the principal diagonal minus 3 into 49. So this will give us, that is 6 2s are 12, 6 3s are 18, that is 192 minus 3 9s are 27, 3 4s are 12, 13 and 14. That will give us 192 minus 147. Now 12 minus 7 is, 5. Now this is 8 minus 4 is 4. So determinant is here, A2 is our 45. Therefore again using Cramer's rule, that says now x2 will be equal to, so I will make it unique from these x1s here. So it is not necessary, we can use only x2, not the bar on the top of this. Now that x2 will be equal to the determinant of the special matrix A2 divided by the original matrix. Now the determinant of the new matrix was 45 here and divided by the original determinant, that is 9. Now 9 ones are and 9 5s are, so this will be 5, implies x2 is equal to 5. So this was all about solving a matrix solution using Cramer's rule. So I will repeat here. Cramer's rule states that this xi, that is the ith unknown variable, is equal to the special matrix which we form divided by the original matrix. Now this special matrix, if we are given a system of linear equations, this first of all we will express these system of linear equations in matrix form by this very rule, that's Ax is equal to B, where A is the coefficient matrix, X is the solution vector, and B is the vector of constant. So this is our A, this matrix is A, and this X is this solution vector, and this is the vector of constants. Now we find the determinant of this matrix, this coefficient matrix. Now determinant, as we have seen in earlier videos, we can use that knowledge here. That is, the determinant of this A is equal to, first we multiply the elements on the principal diagonal, that is 6 into 4, and from it we subtract the elements on non-principal diagonal, that are 3 and 5. So this is 24 minus 15 is equal to 9. Now to solve for x1, if we have to solve for x1, we will replace the column first, that is the column of the coefficients of x1. We replace this column with the column of vector of constants, and from this we form a new matrix, that is A1. So in place of 6, 3, we replace these two elements by 49 and 32. So I have written here 49 and 32, and this is same 5, 4. So A1 is, this is our resulting new matrix. Now we have to find the determinant of this new matrix. Now the determinant, as we have seen, we multiply these two terms, and from it we subtract these two terms or elements here. So this is our A1, that is 36. Now using the Cramer's rule, which says x1 is equal to the determinant of the new matrix divided by the original matrix. That is, the determinant was here 36 divided by the original matrix was 9. So this is 4. Now the value of x1 is 4. Similar cases when solving for x2. And now we have to replace column 2. To solve for x2, we have to replace this column with the vector of constants. That is, we have 6, 3 here. Now we have to change these 5, 4 with this 49 and 32, and we have done this here. We write 49 and 32. So when solving for x2, we replace the second column. When solving for x1, we replace the first column. Now finding the determinant of the new matrix, that is A2, which we got here 45. Now again using the Cramer's rule and solving for the x2, which gives us x2 is equal to the new matrix divided by the original matrix. That is the determinant of the new matrix divided by the determinant of the original matrix. So this is 45 divided by 9, which is equal to 5, and the value of x2 is 5. So this was all about the Cramer's rule. If you like this video, please share and subscribe my YouTube channel, that is Econ Maths. So thank you. Eyvallah kardeş. So for more videos on mathematical economics, please subscribe our YouTube channel Econ Maths. Also like, comment and share if you like this video. Thank you.